So in the previous example, we looked at yearly compounding of interest, which isn't super realistic. A bank isn't going to wait until January 1st to pay you interest. If they did, you would probably switch banks to one that, maybe compounds quarterly or monthly, or even some banks with the new gimmicky daily or hourly compounding that you can see online. Population definitely doesn't wait until the first of the year. If we go back to that world clock, babies are born all the time. They don't wait until New Year's. So we have this concept called continuous compounding, which is where the compounding is happening as we speak, right now, at all times. This isn't super realistic in a bank because when you're writing that computer program, there has to be a certain time interval. But it's great for populations, it's great for modeling the disease idea, it's also good for half-lives when you get into that chemistry example. So compounding continuously, whether you're talking about money or populations, is a different formula. Now, a lot of these are the same. A is still an amount, and P is still a principal. R and T also have the same meaning, but note that R is now in the exponent. R is still our interest rate, and it's still going to be a decimal, and T is going to be time. What's really different is that R is in the exponent, and our base is E. E is not a variable. E is a number. Specifically, E is an irrational number, so like pi, it goes on forever, and its value is 2.718281828 forever and ever, amen. No, it doesn't repeat 1/8 and 2/8 forever, but it is kind of fun for a few decimal places there. So much like pi, E is a number that goes on forever and is really useful in calculations relating to finance and also population modeling. If you wind up in a chemistry class, you can use that E in those half-life problems as well. How long until, for example, a chunk of nuclear waste is half depleted, a quarter depleted, so on and so forth. So continuous compounding is when we don't want to wait until the first of the year to get our money or get our new baby. So let's take a look at this example. Find an amount in a continuously compounded account. Our principal is $5,000. So we want to know the amount if we deposit $5,000. Again, E is our base. Our rate, now we have an annual interest rate of 5.5%. Keep in mind we want that as a decimal, so 0.055. And our time is going to be 4 for 4 years. So much like in the yearly compound example, it is calculator work. We are just going to go ahead and throw all these numbers into the calculator down here. But we do have to incorporate that E in there. So 5,000 is our principal. When you're looking at your calculator, E is on the left-hand side. You'll have to press that blue second key in order to get there, and it's hiding behind the LN button. We'll talk about LN in this chapter as well. So 5,000 times E to the 0.055 times 4 power. Enter. So after those 4 years, this account will be worth $6,230.38. So those are the two applications we're going to look at this point. Try a couple of those out on Math Excel and let me know if you have any questions about where any of the numbers come from, or if you need help with this part, converting whole numbers into decimal numbers, so on and so forth. Let me know what you need, and I'll see you soon.